Hello and welcome to the Motion with Constant Acceleration lecture. We're going to look at what motion with constant acceleration means, and more importantly, we're going to develop some equations that we're going to be able to use to allow us to solve problems involving motion with constant acceleration. Examples would be a car that's accelerating uniformly from rest, or even more importantly or more ubiquitous is any object in free fall if we ignore air resistance. So first up, let's take a look at what we know a graph of velocity versus time for something that is undergoing constant acceleration would look like. We know that this graph, if it's constant acceleration, the slope of this graph is going to be constant. So let's look at something that's got a constant positive acceleration. All right? And we know another equation here, that the average acceleration here is equal to the change in velocity, which is v final minus v initial, all divided by the time that it took. So the other thing that we know here is if we take a look at the average velocity on this, the average acceleration on this line, the instantaneous acceleration at any point isn't going to change. The average acceleration, remember, is the slope of the secant line between 2 points. So if this is v final and this is v initial and this is the time that it took, then the average velocity is equal to the instantaneous velocity at any time. So I'm going to get rid of my bar, and when we have constant acceleration, then the following is true. The acceleration is just equal to v final minus v naught over t. And we can get a function for the velocity at any time t by solving this for v final. So multiplying by t, we've got at is equal to v final minus v naught, and moving the v naught over, rewriting, we've got v final is equal to at plus v naught. And that is a linear equation with v naught being our y-intercept and with a being the slope of the line. So this is our first kinematic equation for constant acceleration. And again, it's very important to note this equation is only true when something is undergoing constant acceleration. So now recall the lab that we did where we watched a cart moving on an inclined ramp. We watched a cart go up, it came to a stop, and then it went back down. And the position versus time graph of that motion, let's say we just look at the motion of the cart going down the ramp, is going to look like that. And we saw that it was modeled perfectly with a parabola. So then our position was modeled by this function, at squared plus bt plus c. And in our laboratory investigation, we found that this coefficient, a, corresponded to exactly half of the linear coefficient from this graph right here. Half of the acceleration, that coefficient, the slope, was equal to a. So I can rewrite capital A as half of the acceleration times time squared. In that laboratory investigation, we also saw that this coefficient b in this parabola perfectly matched the y-intercept from this one. So we can rewrite b as v naught times time, and the c is going to be wherever we started, which is going to be the initial position, x naught. So we put x final in here, and this gives us a function that will find the position of a particle at any time t that's undergoing constant acceleration. And again, it only works when acceleration is constant. These two useful equations together are called the kinematic equations. And it's worth noting once again, only for constant acceleration. And rewriting, and we've got v final is equal to at plus v naught, and we've got x final is equal to 1/2 at squared plus v naught t plus x naught. And sometimes it's useful to have an equation here that doesn't have time in it. So what we can do is solve the top equation for time and plug that into the bottom equation. And I'm going to do the algebra, show it to you on the next page. You can pause it, go through it if you'd like, and then we'll show the result. Okay, so here it is in all its glory. We started up here, we solved the upper equation for time. We got that expression, we plugged that in for time squared and for time, and we did some algebra, and we end up with our equation here at the bottom. V final squared is equal to V naught squared plus 2a delta x. And that is our kinematic equation without time. So let's take a look at an example problem that we might do and use the kinematic equations to solve. So here's our example. I call it the skateboard skid. We've got a kid riding on a skateboard at a constant 5 meters per second, hits a crack, and skids belly first to a stop in 3.2 meters. Yeah, it's going to hurt. What was his acceleration, and for how long did he skid? And we ask, for how long did he skid? We're talking, what was the time? So what I love to do here is I like to make what's called a variable table. And if you'll go back to the kinematic equations, you'll notice that these are our variables all the time. We have x naught, we have x final, we have v naught, we have v final, we have a, and we have t. All right, so those 6 variables are all the possible variables that we can have in the kinematic equation. So I look at my question and I translate the English into math. So I look at what do I know. So a kid riding on a skateboard at a constant 5 meters per second, well, that is his v naught. He's moving 5 meters per second. He skids to a stop. That's v final, 0 meters per second. His initial position, x naught, I can always make the origin, 0 meters. And our unknowns here are we don't know what x final is. Usually if it's what I'm being asked to solve for, I put an exclamation mark. So I'm looking for, oh no, sorry, that's totally incorrect. We know what x final is. It was given to us in the problem, 3.2 meters. He skids that far. It does ask us, what is the acceleration? I put an exclamation mark. It asks us, what was the time that he took to skid to the stop? I put another exclamation mark. Those exclamations mean that's what I'm trying to find. So I know what I'm given. I know what I'm trying to find. The next task is to find a kinematic equation that will relate the knowns to the unknowns. So the last kinematic equation we just derived had acceleration in it. It had x naught, x final, v naught, v final in it. So check, check, check. We're looking for acceleration, and it didn't have time. So I'm going to use that equation. So I'm going to write it down again. It's v final squared is equal to v naught squared plus 2 times a times delta x. And now I'm going to plug in what I'm solving, or what I know. Actually, no, I'm not going to do that. First, I'm going to solve for what I'm trying to find. The variable I'm looking for is a, so let's just go ahead and isolate it. V final squared minus v naught squared, and we're going to divide by 2 delta x is equal to a. Aha, now I can just plug and chug. So here we plug in our values. V final was 0 squared minus initial velocity, which was 5 squared, divided by 2. Delta x is final minus initial, 3.2 minus 0 is equal to a. So let's see here. We've got 25 on top. 2 times 3.2 is going to be 6.4. Oops, and that's negative 25. Be careful, the signs matter. Is equal to our acceleration. Plugging that into the handy-dandy calculator, we've got an answer to 2 sig figs of 3.9. 3.9, and that is negative, meters per second squared. That is the acceleration. And the negative makes sense because the kid's traveling to the right, positive velocity, and slowing down. So velocity and acceleration have to have opposite signs. Next, I need to find the time. I can use the simplest kinematic equation. V final is equal to v naught plus a times t, now that I know a. So solving for the time, we have v final minus v naught over a is equal to t. Plugging in what we know, we've got 5 minus 0 all over negative 3.9. And I did that backwards. Ah, the signs matter. I was going to get a negative time there, and that's never a good thing. Final velocity was 0. The initial velocity was 5. The acceleration is negative 3.9. Now my negatives are going to give me a positive time. 5 divided by 3.9 is 1.3. And that is in seconds. So there's the time. There's the acceleration for this problem. We can solve all sorts of stuff. My recommendation, make your variable table, fill it in, figure out what you know, what you're trying to find, and pick a kinematic equation or two that will get you there. The most common example of constant acceleration motion is free fall in the absence of air resistance. If it's short free fall or if the object is heavy enough, we can generally ignore air resistance, which means that the acceleration is constant. And the acceleration in constant is equal to what we call little g, the acceleration due to gravity at Earth's surface. And we will use the standard 9.8 meters per second squared in our calculations in this class. But please be very careful because the direction of this acceleration is going down. So it is actually negative 9.8 when we plug it in. These free fall problems are actually somewhat easier than the linear motion problems, the horizontal motion problems, because we always know the value of the acceleration. When I'm filling in my variable chart, it's always going to be negative 9.8 meters per second squared. So it's really, really nice. So the kinematic equations become V final is equal to negative 9.8 times time plus V naught. And also we could say X final is equal to negative 4.9, because that's half of A here, T squared, plus, that's not a plus, that's a minus. No, it's not, it's V naught. I'm getting confused. I shouldn't be. Plus V naught times T plus X naught. And the final one becomes V final squared is equal to V naught squared minus 2 times 9.8 is going to be 19.6. And the negatives, again, are coming from negative 9.8. 2 times A times delta X here. Oh, and I should actually also mention that we're not dealing with horizontal motion anymore. We're dealing with vertical motion. So let's put a Y final in here and a Y naught in here and a delta Y in here, because we're talking about vertical motion and we use Y's. So the problems are going to work the same. It's just we put in negative 9.8 for the acceleration every single time. Be very careful with your signs, because your signs are going to either screw you up or give you the right answer. So double check your answers to make sure they make sense. I'll see you next time.